Okay, the very first question, we have to find out E and G naming system. So we have very clear information when two high priority groups are in same side. So G means same side, and E means anti side. So this double bond, look at, and here we have a hydrogen. So now between carbon and hydrogen, this carbon has higher priority. And look at this carbon, this is CH3, this is CH3. Here we have a single hydrogen, and this is carbon having two hydrogen. So the very first atom carbon is same, and here this carbon is bonded with two more carbon and one hydrogen, like this carbon and one hydrogen. And here this carbon is bonded with a single carbon. So carbon and again hydrogen, HH, and again this carbon. So if you compare, this one has very first atom carbon, so this bond has more priority. So this is my one. So now you can see both high priority in the anti side. So this would be E. Make sense? Please tell me, everyone. It makes sense, the very first one. Very good. Now look at this double bond. Now tell me, between the ring and this trimethyl, which has more priority? This alkyl chain and the ring, which one has high priority? Just tell me one by one. My question is, this ring or chain, which one has high priority? Always compare each atom one by one. Look at, if you compare this carbon is same. This carbon and this carbon is same. Now the next, it has two more carbon and it has three direct carbon, you can see. So the chain has more priority than the ring. So this is my one. And here this is CH3, the carbon same. And again this carbon is bonded with two carbon and this is bonded with hydrogen. So this bond has more priority one. So you can see here both high priority groups in the same side. So it would be G. It makes sense? Try C1. Please tell me, everyone. What should be C? Take your time and tell me the C1. Look at here. The very first atom here carbon and here carbon. Now this carbon is bonded with two carbon and here oxygen. So between carbon and oxygen has high priority. So this between them, it would be my one. And here fluorine and the methyl. So if you compare, this one would be my first. Okay. So we can say both high priority groups are in same side. So it would be G. Make sense? You have to compare this and this. So it would be G. What about D? Look at here. Here we have hydrogen. This is methyl. And this is chlorine. This is CH2. Between methyl and H, methyl would be 1. Between chlorine and CH2, chlorine would be 1. Both high priority in the same side. So it would be G. Make sense? Tell me, everyone, it makes sense? Any doubt about problem 1? A, B, C, D?
I have a question.
Yeah, say.
So whenever you're looking at the alkene, you look at the ones that are opposite sides and then you compare, not on the, like, they don't have to be on the same side, right? To be the priority. Is that like what
Yeah,
you're saying?
I am saying, suppose this is my carbon, double bond carbon,
Mm-hmm.
and I am saying this is 1, this is 2, this is 3, this is 4. Assume these one are the groups. Assume these one are the groups. I am not saying which one has high priority or which one has lower. I am just saying, okay, we can say that suppose this is A, B, C, D.
Okay.
A, B, C, and D. Now you have to compare the priority of this side, like which one have high priority. Suppose B has
Mm-hmm.
high priority. Now compare C and D, which one have high priority. Suppose C have high priority. Now you can see these two have high priority and these are in same side, downside. So it would
Okay.
be Z. And if
Okay.
high priority groups like this one and this one in NT side, so it would be E. Make sense?
Got it. Yes, makes sense. Thank you.
Okay, now move to the R and S configuration and we have wedge and dash and Fisher projection. So I discussed in video how to figure out R and S in a very simple way. So I told you the rule, dash. D indicates lowest on dash, lowest on dash. A indicates anti-clock and S would be configuration. So if lowest on dash, moment anti-clock, configuration is S, it means dash clock would be R. Clear? Similarly, we can apply for wedge as well. So just opposite, wedge NT, what it should be? R or S? Look at, if dash NT is S, so wedge NT would be R. If dash clock is R, then wedge clock would be S. Simple. So here we have this chiral center. Here wedge is OH, so dash would definitely be H. Now decide the priority. So whenever you have a group, compare the very first atom in each group. So this oxygen would be 1, hydrogen would be 4th. Now look at this carbon, this carbon. The very first carbon is same, but it bonded to the nitrogen and it bonded to a carbon. So between carbon and nitrogen, nitrogen has more priority. So this bond would be my second and this one would be 3. Now my lowest on dash, lowest on dash. Now move 1 to 2. We can cross the fourth priority. So 1 to 2 going clockwise. So dash clock, which means R. So this would be my R. Make sense? Please tell me. Everyone, it makes sense? Okay, now look at this chiral center, this one. Here wedge is my methyl. The dash would be hydrogen. Now decide the priority. Let me zoom this. Okay. So this carbon has the very first atom nitrogen here hydrogen, here carbon, and here the left is carbon as well. So nitrogen has more priority because highest atomic number, so 1. Hydrogen would be 4th. This carbon have OH, so this would definitely 2, and this would be my 3. Now move 1 to 2. So this is the movement of 1 to 2, and it is going anti-clock, lowest on dash. So dash NT would be S. So this would be S. The second chiral center would be S. This is S. Make sense? Tell me everyone, it makes sense? Yeah, please reply everyone. Okay, now look at the B. This chiral center. Okay, which one is my first priority? Chlorine, CH2Br, this CH2, or the left hand side double bond? Which one? Look at here again. Whenever you have a group of atom, always compare the very first atom. Here chlorine, this is the carbon, then bromine, okay? This is the carbon, this is the carbon. So chlorine would be my 1. This CH2Br would be my 2. Clear? And this would be my 3. Why? Because this CC common, next is chlorine, and next again here the carbon linkage, and this is my 4th. So let me write down this. Carbon wedge is my first priority, dash is my second priority, the right side plane bond would be my 4th, the left side plane bond would be 3. Make sense? Please tell me everyone, this priority makes sense? Very good. Now we have the rule for wedge and dash only. It means when the lowest on either wedge or a dash. We don't have a rule when the lowest on a plain bond. So this 4th priority is my same plane, not wedge, neither wedge nor a dash. So do you know the rules for this? Please tell me everyone. Do you have any idea what should I do? If you have any idea, just let me know. Yeah, very good. Someone is saying rotation. Could you please explain? And you can turn on your mic. I would like to hear you. What kind of rotation do you want?
I think that
Yeah.
one is the one that you
Yes.
basically rotate it on the axle.
Yeah, very
So,
good.
so
So
you switch the groups on the sides.
yeah, that's fine. Yeah. So lowest is my plane. So now I am going to keep lowest on dash. Okay, like this. I'm not going to change anyone. Wedge 1. Dash would be my, I'm going to put the 4th on the dash. And the plane bond as 2. And this is my 3. This is an odd exchange. Odd means just one exchange, the exchange of 4 and 2. So whenever we have odd exchange, then we will flip the answer. If suppose we got R, then the answer would be yes. If we got S, then answer would be R. Because after odd exchange, compounds configuration would be different. So now my lowest on the dash, now move 1 to 2, 1 to 2 going clock. And we know that clock is generally R, but we have a switch. So R becomes S. So this is S. Make sense? So you can apply this rule whenever the lowest on the plane bond. Okay.
So I have a
Yes.
clarifying question.
Yeah.
So if it's not on a dash, the 4th one, you have to flip it. Is that what it is?
Yeah.
Okay.
Then the lowest is supposed to be neither wedge nor dash in a plane bond, single bond. Then you can keep 4th on the wedge or on the dash because we have the rule for wedge and dash. Make sense? Okay. What about this one? Here bromine on the dash, hydrogen on the wedge. What about this one? Tell me, R or S? Take your time and let me know. Okay, bromine first priority, 4th hydrogen, and here carbon chlorine would be my second and this is the 3rd. Now move 1 to 2, we can cross the 4th priority. So 1 to 2 going anti-clock, okay? So which anti is S? No, wedge anti is R. You can check the rule. Wedge anti R. So this would be R. Clear? Means whenever the lowest on the wedge, you can just flip your answer. If clock is R, then it would be S. If anti-clock is S, then it would be R. Make sense? Whenever the lowest on the wedge. Okay. Let's try this Fisher projection. You know, the dash and vertical have the same rule. It means when the lowest on dash or when the lowest on vertical axis, clock would be R, anti-clock would be S. So someone is saying it only for wedge, not dash right to. Yes, when the lowest on the wedge, then you can flip your answer. Or you can memorize the condition or you can flip. Now look at the C. So bromine 1, oxygen 2, this down bond would be 3, hydrogen 4th. Now move 1 to 2. So 1 to 2 is going anti-clock and the lowest on vertical axis. So I said that vertical and dash have the same rule. So dash NT is S, so vertical NT is also S. Make sense? Tell me everyone, it makes sense, the first one? Okay. Now tell me the bottom one. Chlorine 1, nitrogen 2. This upper bond would be my 3 and this would be 4. So wedge and horizontal have same rule, means flip your answer. So 1 to 2, 1 to 2 is going anti-clock and we know that NT is generally S. So flip your answer, it would be R. Make sense? Tell me everyone, it makes sense? Okay, what about this one? What about this one? The last one. Find out R and S. And again, we don't have lowest on wedge and dash. So you have to keep the lowest on dash and figure out answer. Whatever the answer, you have to flip. We can decide the priority. Chlorine 1, oxygen 2. This bond would be 3 and this is my 4th. So dash 1, sorry, dash 2, wedge 1, right side 3, left side 4. So I am going to keep 4th on the dash. So 4th on the dash, it means second on this position. So this is second wedge and this is not going to change. This is 1 and this is 3. So 1 to 2. 1 to 2 is going anti-clock. So NT is S. So flip your answer. So it would be R. Make sense? Please tell me everyone. It makes sense?
So whenever you flip it with the dash, not the wedge, right?
Your choice. It's your choice. You can fix with the wedge as well. But you know that
Okay.
for the wedge you have to flip 2 times because wedge have opposite rule and again you have to keep opposite. It means 2 times you can fix wedge.
Oh,
Okay,
okay. So
let me explain with the wedge switching. Let me explain. So I'm going to keep my 4th priority on the wedge. So dash second, wedge would be my 4th. So this would be 1 and here 3. So 1 to 2 going clock. Generally clock is R but lowest on the wedge. So this is S. And I said that whatever you have answer, just flip. So S becomes R. Make sense? Okay. Now the next question, identify all chiral center in each of the following compound. So you have compound 1, take your time and let me know how many chiral centers. Tell me everyone. Okay, no need to check chirality over CH3, CH2, carbon double bond, carbon triple bond. This is CH2, this is CH2, this is double bond, this one is a double bond, this one is a double bond. Okay, so now the points which is left, this and this. These 2 points we have. Whenever you have to check chirality, always look at the entire length. Do not compare the very first atom in all the side. Means look at this position. This one has OH, this one have H. The left side we have CH2, CH2, OH. Okay, CH2, CH2 and OH. And the right side we have a ring with oxygen. So it means this carbon have 4 different side chains. So this one is a chiral. Makes sense? This one OH containing carbon. Please tell me everyone. It makes sense?
So it's just one chiral or two
Yeah, let
chirals?
me explain this one as well. This one.
Oh, okay.
So here we have a hydrogen. So now look at this hydrogen different, one side oxygen different, two different, and downside you can see the carbon containing OH and the left side entire chain. Do not compare this COH, COH. No, I said that always compare the entire length. The downside we have this kind of structure, and the left side we have this kind of structure bulky. So these two lengths are different, hydrogen different, oxygen. So it means this one is also chiral. It makes sense? Please tell me everyone, it makes sense? Okay. What about the B? How many chiral center in compound B? So here we have 2 chiral center. What about compound B? Yeah, very good. Perfect. Look at this is not chiral because the left ring and the right ring is identical. So 2 same sides. Now look at this position. This upper carbon chain is definitely different. Hydrogen is different. But now look at the left and the right branch. CH2, 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 CH2. And then nitrogen is common for both. So this carbon is not chiral carbon. Okay. And now look at this OH containing carbon because we don't have to check over here and here because this is CH2, CH2. This is CH3. This one is a hydrogen. So CH3 different, H different, OH different. This chain is different. So this one is chiral. So we have one chiral center. Make sense? Please tell me it makes sense. Perfect, perfect, perfect. Try C. Okay, let me ask one by one. Okay, I'm going to start. I am going to start from this position. I'm going to start from this. So is this chiral? Yes or no? Just tell me yes or no. Very good. No means N, yes means Y. Okay, so don't waste your time. What about this? Yes or no? What about this? Yes or no? This, this, this. Okay, what about this one? Yes, the entire chain is different. Here we have a hydrogen. So I'm going to keep it star. What about this? Yes, this one also chiral. Okay, what about this? This one? This one? This? Okay, what about this? Yes, very good. What about this? Perfect, perfect. And this? This one? This one? Yes. So how many? 1, 2, 3, 4, 5. Okay. So we have 5 chiral center. If you guys have a doubt on any of the center, I'm going to mark 1, 2, 3, 4, 5. If you have a doubt on any position, just let me know. You have 10 seconds. So if you have a doubt on any of the carbon, which is chiral here, just let me know. I'm going to explain. If it's fine, then perfect. All done? Carbon 2, someone is saying, okay, this is methyl, different, hydrogen, different. Now I said that always compare the entire length. Try to understand what I'm trying to say. Compare entire length, right, left, up and down. So do not compare this is CH2, this is CH2, no, this is same, so how can it be chiral? No. If first atom is same, move to the next. This is CH2, okay, this is now CHOH. So this is different, makes sense? The left and right is different from the bottom as well. So this is chiral. All done? Okay. Now next is cis and trans we have to identify. And here I have the double bond A, B, C, D. Now I have a question A. What about A, cis or trans? If it's not available, then let me know. There is another option not available. I discussed the condition of cis and trans in my video and I said that any double bond can show cis and trans when both the carbon have different chains. Means this carbon should be different connectivity like methyl and H. They are different from each other. And this carbon also have different connectivity, methyl and H. So this one is different. So it can show geometrical. If any of the carbon have same connectivity, then it would not show geometrical. So what about A? Cis trans not available. Let me know. Yes, not available because this carbon have two same methyl. So not available. What about D? Cis trans not available. D, D, D. Okay, balance the double bond. So this carbon have two hydrogen. And this is CH2 and this is H. So the left carbon has different connectivity, but the right have same. So again, not available. It makes sense. What about B? Cis or trans? And one more thing, Z is equivalent to cis, E is equivalent to trans. Okay, B is definitely showing cis and trans, but which form is this, cis or trans form? Okay, look at here. Here we have a hydrogen, and you know that between CH2 and hydrogen, CH have more priority downside. And here this is CH3 and this is CH3. So downside has more priority than methyl. So both same side means Z. Z is also equivalent to cis. Now look at the C. Here we have H. Here we have H. Both hydrogen in the anti side, opposite side. This is trans or E. Make sense? All done? Please tell me everyone. It makes sense? Okay. Now we have a question. Identify whether each of the each of the following pair of a compound are enantiomer or diastereomer. So we have two rules to figure out the enantiomer and diastereomer. The very first was flipping. If one chiral center remain unchanged and one chiral center have a change, that is called diastereomer. If both the chiral center have change, then it would be enantiomer. Change means if wedge become dash, dash becomes wedge. For example, if you look at pair A, you have two methods. You can do R and S or you can look at the exchange. So this is not the mirror image first of all. If you want to draw its mirror image, means if you want to keep a mirror here, then it should be like this. This is the mirror image. Make sense? So suppose this is compound 1 and this is compound 3. So this is the direct mirror image. So whenever you have a mirror image, then we can say directly it is enantiomer. So first and second compound, if you compare, this is not mirror in the right hand side. This is not mirror in the right hand side. Now look at the axis change. This is methyl here, wedge, and this is dash. This is dash, this is wedge. So this is a kind of opposite as well, like wedge becomes dash and dash becomes wedge. So this is again a mirror image kind of thing, but it is not a mirror in the right hand side. This is a flipping, you can say, just odd exchange. Odd means just one exchange. So wedge becomes a dash, dash becomes wedge. So this is called enantiomer. Make sense? Tell me everyone.
So it's not identical?
No, it's not identical.
Okay.
It could be identical if you are going to change two things. Two things means suppose I am going to keep mirror image as well as I'm going to flip the axis as well, like this. This is wedge becomes a dash and this dash becomes a wedge. Now 1 and 3 are identical because it's mirror image plus axis change as well. So we have overall two exchange, one in terms of mirror image of the structure and second axis interchange as well. So overall it's even kind of exchange. So even always produce identical. For example, suppose we have this compound. This is supposed to be OH. Now I have to draw enantiomer of this molecule. So the best way to draw enantiomer is keep everything same, change wedge with dash. So 1 and 2 enantiomer. Make sense? It makes sense, this one? Okay. Now look at this one as well. Suppose this is my wedge OH. What is this? What is this? if you are going to keep a mirror here, then you can say these are just a mirror image. And mirror image is also considered as enantiomer. So this is enantiomer. Try to understand the concept here. If I am going to keep structure mirror image as well as axis change, then it would be overall two exchange, one with the compound mirror image and second axis change. Then it is overall identical. Means if I'm going to keep here like this dash OH, so I changed this one and structure mirror image as well, like this plane. So this is overall two exchange and two is called identical. So this is identical. So 1 and 3rd is identical. Make sense? And same thing here, you can see. This is not a structure mirror image, the 1 and 2. It is just axis change, means wedge become dash, dash becomes wedge. So this is what? Enantiomer. Make sense? Okay, what about B? Now look at here. Yes, odd always be enantiomer. Now look at the B. Here we have two chiral center, two chiral center. There is a change with respect to one chiral center, top to top. And there is a no change in the bottom. So when I said that when there is a exchange of only one chiral center and rest remains same, that is diastereomer. So this technique can save your time. You have two methods to find out the relationship. One is RS method, but it takes some time because you have to find out R and S for means 4 chiral center and it takes some time. But if you are going to apply this kind of rule, then it would be easier for you. Make sense? Okay. What about this one, C? Now look at here, this and this, there is no change. Make sense? This is X, no change. Here chlorine on the wedge, hydrogen on the dash. Here methyl on the wedge, hydrogen on the dash. This is methyl. This is methyl. So now you can see one chiral center have no change. Can you see? And one chiral center have odd exchange. You can see there is exchange of chlorine with methyl. So what is the relationship? Tell me. If one has change, one has no change, then that is called diastereomer. Make sense? Tell me everyone, it makes sense? Okay, perfect. Now look at this compound. You can find out RS for all the 3 chiral center. You can see this wedge has wedge OH, no change. But there is a change with respect to this and this chiral center. Make sense? So it should be diastereomer. Okay. And one more thing I would like to tell you. Do not fix on any of the rule. You should be flexible with the rules. If you think I am not strong in flipping or mirror image, then you can apply RS method to cross check your answer. Okay. So there is no change with respect to this. Now find out the R and S for this configuration. This is wedge methyl. So dash would be my hydrogen. Now you can find out the R and S for this. So this carbon with the OH has first priority. This CH2, CH3 have second priority. This methyl have third priority and hydrogen on the dash. So move 1 to 2. 1 to 2 going anti-clock, so NT means S. NT is S. What about this? What about this? Tell me everyone, what about this? Dash is my methyl, wedge would be hydrogen. So this carbon having OH has 1, downside 2, methyl 3, hydrogen 4. 1 to 2 going clock, lowest on wedge. So flip your answer, R becomes S. So this is S because lowest on wedge. Okay. Okay, now we will figure out this OH as well. This chiral center, the R and S, this one. This wedge OH and wedge methyl. I am going to find out this one. So 1 OH, this bond would be 2, this is 3, hydrogen is 4, 1 to 2 going clock, clock is R. So this is R. Now find out this one. Find out this one, what it should be. You can see wedge is my OH, dash is my methyl. So here dash is H. So 1, this is my 2, this one 3, this one 4. 1 to 2 going anti-clock, lowest on dash, no need to flip. So this is S. So now you can see this R, this is S. There is a change in one chiral center, but the second, this S becomes S. There is no change. So no need to check the last chiral center R and S. Whenever there is a mixing means like one has no change, one has change, then it would be always diastereomer. Make sense? Please tell me.
So for enantiomers, it would be opposite, right? So it
Yes,
would be
always
RS,
opposite,
RS.
always opposite, and with respect to all chiral center, it would be opposite, not
Okay.
any one of them. So if all the chiral center have same configuration, identical. If all the chiral center have opposite configuration, enantiomer. If there is a mixing of same and opposite, then diastereomer. Makes sense?
Okay,
Now
so
look,
what if it's like S and S and R, that's identical, right?
yeah, if you have same configuration, like suppose this wedge OH is here R and here suppose OH is R, same. Suppose this is S, this second is S as well, and the third one is also you have to check. Suppose S and this one also S, then they are all identical.
Got it.
Okay, what about this E? Now look at here. Here we can apply the exchange method very easily. No need to check R and S. Now look at here. This remains same, there is no change. Here wedge is my methyl, dash is methyl, wedge is hydrogen. Here dash is ethyl, wedge is my hydrogen. So you can see there is an exchange between this and this. And this one remains same. No change, same. And this one is exchange. So this is a diastereomer. Make sense? Please tell me everyone. And you can apply RS as well, okay? Identify whether each of the following compound chiral or achiral. So let me tell you one thing. Chiral means if anyone have chiral center, and achiral means no chiral center, and plane of symmetry. Okay. And one more thing I would like to tell you, whenever any compound have exactly one chiral center, and look at my language, exactly one chiral center, only one chiral center, then it would always be chiral and optically active. Generally, chirals are optically active and achirals are optically inactive. So look at this one compound A. So you can see here we have two chiral center and there is no plane of symmetry. Do you know what is plane of symmetry? Plane of symmetry is a, are going to talk about me. We will discuss meso later. Okay, meso means minimum two chiral center and having plane of symmetry. Again, listen me, what should be the condition of meso? At least two chiral center should have plane of symmetry and they are optically inactive. Okay, so if you have these conditions, then that particular compound would be meso. So look at compound A. It has two chiral center, but there is no plane of symmetry. Plane of symmetry means it is a hypothetical plane which can divide the molecule into equal halves. So there is no plane of symmetry. Clear? So if you don't have a plane of symmetry, then it means it would be chiral. So this is chiral. Any doubt? Please tell me. It makes sense? Okay. Now look at the B. How many chiral center in B? I am telling you, we will discuss meso later. The compound A is not meso. Meso means optically inactive and meso must have plane of symmetry. But compound A have no plane of symmetry, okay? So, okay, what about compound B? How many chiral center? Just one. And I said that whenever you have just one chiral center, it means no plane of symmetry and it would always be chiral. So this is chiral. Okay, what about C? How many chiral center in C? How many chiral center in C? How many chiral center in C? You guys always confuse about wedge and dash. Look at the groups. Do not confuse about wedge and dash. Look at the group. This is methyl. This is also methyl. So how can you say this carbon is chiral? If you don't have a chiral center, it means it would be achiral. So this is achiral. Why? Because there is a plane of symmetry. It can divide the molecule into equal halves like this. Okay, what about the D? D. How many chiral center? How many chiral center? Yeah, very good, two chiral center. Now look at the trick here. Now look at the trick. Look at this. This carbon length is like this, Z type. So I would like to rotate the carbon length in this manner, like this. So this is my number one, this is number two, this is number three, this is number four. 1, 2, 3, and 4. Now number 2, OH would be wedge. But I am going to rotate this one here. So if this bond is going down, this bond is going down. So OH on the wedge here, it is downside. So it would be dash in the upside like this. Try to learn the rotation here. This is very important concept. So if you are going to rotate this molecule 180-degree angle, so if you are going to fix this 3-4 bond downside, then the OH would go up and it should be on the dash as well. And you know that here we have two chiral center, but we don't have a plane of symmetry here. So if no plane of symmetry, it means chiral. Make sense? Now look at this E1. Again, this is Z type, so I would like to convert this structure like this. This wedge OH would remain same. But if you keep this over here, so dash will become wedge. So wedge OH. And now we have two chiral center, plane of symmetry. So this is achiral and achiral is, and it is like a meso as well. Why? Because two chiral center and plane of symmetry. So this is meso structure as well. It makes sense? Please tell me, everyone. Okay, what about F? Let me know F. Any plane of symmetry? Plane of symmetry means which can cut the molecule into equal half. Any plane of symmetry? Yes, look at this. So left and right exactly same. So plane of symmetry means achiral. Okay. Yeah, means you can cut from here. And do not check the wedge and dash of this axis. If this is wedge or dash, it doesn't matter because we are going to cut this axis. Okay. So always compare the left, right, up and down part of this axis. Do not check atom which is connected to this axis. Same here you can see G compound. If you look at G, you can see there is no chiral center and you can cut from here. Do not check the group bonded to the up and down side because this is in the axis. Now left and right is exactly same and there is no chiral center here as well. So this is achiral. You can check this molecule again here. Okay, let me know how many chiral center here. Any chiral center? Chiral center means 4 different things. This is wedge methyl dash H. This carbon has 2 different things. That's fine. But the left and right is exactly same till the end. So no chiral center and no chiral center means achiral. Make sense? Okay, what about K? We have 2 chiral center. Plane of symmetry. I said any plane of symmetry here. Yes, this, look at. Clear? And same thing in the I as well. Look at here. If you are going to cut from this axis, now you can see this wedge methyl and this wedge methyl. This is same. So we have a plane of symmetry. So plane of symmetry means achiral. This one also achiral. Any doubt? Tell me everyone, any doubt? Okay, now look at this H. I think we left the H one. So if you look at the H, you can see chiral, 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 and there is no plane of symmetry. If you are suppose going to cut from this axis, then this is the wedge, but there is no wedge. So no plane of symmetry. So this means chiral. Any doubt? Tell me everyone, any doubt? Now look at I, chiral center, chiral center. And again, there is no plane of symmetry, no plane of symmetry. And no plane of symmetry means chiral. Make sense? Okay, what about I? How many chiral center? How many chiral center? This one, I am talking about this compound. How many chiral center? Again, I am telling you guys, always look at the entire length. I don't know why you guys are confused. OH different, methyl different, that's fine. But the left and right is exactly same till the end. You can see. Look at here, CH2, 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 CH2. This CH2 is common for both. So if no chiral center, it means achiral. Make sense? Tell me everyone, it makes sense? Okay. Now the next is identify the meso compound. I told you the condition for meso. At least 2 chiral center, and second must have plane of symmetry. I told you the condition of first one. This is Z type, so we will try to make like this wedge OH. Now let me know, this wedge becomes dash, and now we have 2 chiral center. Is there any plane of symmetry? There is no plane of symmetry. Plane of symmetry, we can say if wedge OH, like this, wedge OH and wedge OH. So this is divisible into equal half. So we can say this one is meso, but this is not meso, okay? No meso. Make sense? What about the second one? We have 2 chiral center and there is a plane of symmetry. So meso. Make sense? Yes. What about this one, third? Third. Take your time, let me know. This is very good example. Do you think how many chiral center here? How many chiral center? Tell me honestly, how many chiral center? And I told you the condition, at least 2 chiral center. This is not the chiral center first of all, because the left CH2H, right CH2H, exactly same. Yes, there is a plane of symmetry, no doubt. So this one is not meso. This is achiral. Make sense? Tell me everyone, it makes sense? Perfect. Okay, now we have a question here. What is the nature of the following compound optically active and optically inactive? So optically active generally have a chiral center. Chiral center. And no plane of symmetry. No plane of symmetry. And optically inactive means plane of symmetry, as well as you can say no chiral center. But this is in Newman projection, so how we can do this? So we have to convert this Newman projection in the Fisher projection. I discussed how to convert the Newman into Fisher in my video. So let me tell you here as well. Look at the front carbon. The dot one is my front carbon. So if you look at the front carbon, you know the up is OH, up is OH. The right side we have a hydrogen, so keep right side we have a hydrogen. Now the left side we have methyl, so left side we have methyl. That's fine. Now look at the rear carbon. This is the rear one, the circle one. This is the rear one. The downside OH, keep downside OH. Now this is methyl, this is hydrogen. Now one more thing I would like to tell you here, a trick. Whenever you are going to convert Newman into Fisher, then one chiral center would be same. Like here the front remains same. But whenever you are going to draw the rear one, always flip 2 groups, always. Because Newman is nothing, it's is eclipse form of Fisher. It is eclipsed form of Fisher. So you have to draw the eclipse form. Okay. And this is the staggered in the Newman projection. So if you are going to do eclipse, it means you can flip the groups. So here you can say methyl in the right, hydrogen in the left. So I would like to change them. Methyl in the left, hydrogen in the right. And now you can see you have two chiral center. There is a plane of symmetry. And whenever we have a plane of symmetry, then it would be optically inactive. So this is optically inactive. Make sense? Please tell me, everyone. Would you like me to discuss this again? Would you like me to discuss this again? Okay. Okay, I got it. Now look at here, the black point. This is my front carbon. So I'm not going to change the front carbon, the positioning. So OH is up, hydrogen is right, methyl in the left. That's fine. Now you can see this rear carbon, these two OH in the opposite axis. So I'm going to keep OH here down. Now I will interchange this methyl with this hydrogen because I have to draw the eclipse form. So I am going to exchange both of the groups. So methyl is going in the left and hydrogen in the right. So this is my correct drawing of the Fisher projection from the Newman. And you can see we have two chiral center, but there is a plane of symmetry. So whenever plane of symmetry, it means it looks like meso, and meso compounds are optically inactive. So this is optically inactive. Make sense? Now look at the second one, B. I am going to keep the front one same, ethyl. The right is methyl. The left is H. Now look at the rear carbon, this circle one. Hydrogen down, keep hydrogen down. And now I'm going to switch chlorine with the methyl. So chlorine is right, so keep chlorine in the left, methyl in the right. So now you can see there is a two chiral center we have. Any plane of symmetry? Tell me everyone, any plane of symmetry? No, so if you don't have a plane of symmetry, it means it would be optically active. So this is optically active. Any doubt? Any doubt? Perfect, perfect, perfect. What about this one? Two chiral center. Any plane of symmetry, tell me. Any plane of symmetry? No plane of symmetry. So no plane of symmetry means optically active. Clear? Make sense? Perfect. Now look at the chair form. I have done this in my video how to convert chair into ring form. But don't we rotate them? Yes, because this is not in Newman. Okay, this is direct Fisher one. So no need to rotate. Whenever you have a Newman, you have to convert in Fisher first. And in Fisher, you have to draw its eclipse form. That's why we can switch both the groups. But it's a direct Fisher one, so no need to rotate anything. Okay. Now look at the conversion of chair into ring. This is chair form. So this is the ring form. This is 1-2 position. The groups are located at 1-2 position. So this is 1, this is 2. Now this is up. So whenever the bond is up, you can represent through wedge. You can represent through wedge. So this is wedge. Okay. This is axial up. This is axial up. And if you look at 2, what is the nature of this bond? This is equatorial. Now let me know, is this equatorial up or equatorial down? Tell me. Equatorial up. Yes, this is equatorial up because the axial down is this one. This is axial down. So this is equatorial up and up is again wedge. So again 2 is wedge. So you can see two chiral center and having plane of symmetry. So whenever you have a plane of symmetry, optically inactive. Make sense? Tell me everyone. What about this one? If
So
suppose
it
you,
would,
yeah, say.
sorry. So it would cut down in between 1 and 2, so that's
Yes,
why
yes,
that's the
yes,
plane of symmetry, right?
yes, yes.
Okay, just making sure.
If we have this one, suppose. What about this? Optically active or inactive? Look at here. This is up, so wedge. This is down, so dash. So no plane of symmetry, so optically active. Make sense? It's all about the concept. Here we have two chiral center. That's why we are thinking about plane of symmetry. What about this one? What about this one? Optically active or inactive? Okay, how many chiral center? How many chiral center here? Look at here. It's super simple. Look at this is 1, this is 2, this is 3, this is 4. So if you convert the ring, the groups are located at 1 and 4. It doesn't matter what should be the stereochemistry of 1 and 4. Wedge, wedge, dash, dash, wedge, dash, nothing. You can just cut the molecule into equal half. So no chiral center having plane of symmetry. So plane of symmetry means optically inactive. Makes sense? So whenever the groups are located at 1, 4 position, always have a plane of symmetry. Make sense? Like here, this is divisible into equal half. So plane of symmetry. So optically inactive. What about the G? G, yes, divisible into equal half, plane of symmetry. So optically inactive. Make sense? You know, in DAT, four type of stereochemistry questions are very common. The very first question, whenever you have any isomer, suppose A and B, look at the options. If any of the option have constitutional isomer, if any of the option have constitutional isomer, then do not neglect the option. Always compare the molecular formula. If molecular formula is same, then try to name the compound means IUPAC or look at the structure. If structure is different or IUPAC naming is different, then it would be constitutional isomer. If name is same, the structure just like supposed to be same, then it means different. Then it could be a stereo as well. You can think about a stereo. Make sense? For example, look at this compound. What is the nature of A and B? What kind of isomer is this? Constitutional, identical, enantiomer, diastereomer. Tell me. You guys should hang me. Yes, you should hang me. I told you, look at the compound, look at the groups. This is 1-2 position. The chains are at 1-2 position. And here this is 1-3 position. There is a difference in the naming. The name of the first compound would be 1-2 dimethyl cyclohexane. And this is 1,3 dimethyl cyclohexane. So whenever you have a different name, it means structure different, and that is always be constitutional isomer. Make sense? This is just like a trap. Means you can represent the structure in wedge and dash, and you guys get confused it is a stereoisomer. No, always take your time. Try to start from the basic. Make sense? Tell me everyone, it makes sense? Yes or no? Okay, let me give you another question. Maybe this is also a trap for you. I'm just telling you trap. I'm not saying like trap. It can be easy one as well. It's all about the concept. Now there is options. This is compound 1, compound 2. You have to tell me the relationship between them. The very first option is epimer. Second option constitutional isomer. Third option diastereomer. Fourth option identical. Last option in enantiomer. Now tell me. Epimer is just basically applicable in carbohydrates. So this is just a as an option here. Okay, epimer is nothing. It is not related with this compound basically. It's just an extra option for you. Okay, you guys look at here. Is this chiral center? Tell me, is this chiral center? Yes or no? Is this chiral center? Yes or no? The bottom one in the first. Yes. So it means if you are going to write down the first compound, then we can say this is CH2Br and this is H, this is OH, this is methyl. So we have one chiral center. Now look at the top one. This is again no chiral center, CH2Br, OH, H, methyl. So chiral center. Now you know that if you don't have a double chiral center, means just single chiral center, then how can you say diastereomer? Because diastereomer is applicable in cis trans as well as multiple chiral center compounds, more than one chiral center, not a single chiral center. So now you have two choice, identical or enantiomer. And I told you the rule, the exchange rule. CH2Br, CH2Br, same position. CH3, same position. There is exchange of H and OH only, odd exchange. And whenever we have odd exchange, it means enantiomer. So answer would be enantiomer. No need to flip. Oh, sorry, no need to figure out the R and S method. Okay. It makes sense. So whenever you have a question, try to break down the question in a simplest form. If I am going to give you this question in this form, then I am very sure 99% student can answer this. Make sense? Okay. Now look at this one. I am going to discuss only few questions with this sheet. What about this? These two compound A and B. What are the relationship between them? Position isomer, chain isomer, The stereoisomer tautomer. So tautomer, it's not tautomer basically. And you can see this compound have a different name, because if you start the numbering, you know that this is one ketone should be 2, this is 3, this is 4. So name would be 3, 3 dimethyl. 3 dimethyl this is. And if you name this compound, both the side ketone would be number 3. So you can start from this in where the branch get the lowest 2, 3, 4, 5. So this is 2 methyl. So 3 methyl, 2 methyl, which means name is different. So name is different means constitutional isomer. So stereo is not right. So now you have position and chain. So what is position isomer? Position means whenever there is a difference in the position of functional group, position of double bond, So here ketone at number 2 and here ketone at number 3. So this is positional isomer. Clear? Tell me.
So what would a chain isomer be like?
Chain is just like difference in chain. For example, suppose you have 6-member ring and now I am saying 5-member ring with one branch. So chain is also considered as branch. So this is chain and this is chain isomer. Or you can
Okay.
draw 4-member ring with 2 branch. So this is also chain isomer. Chain is basically a part of constitutional isomer. I have discussed in a very detailed way the type of constitutional isomer. Type of constitutional means chain, position, functional isomer, and there is a one tautomer. This is a part of constitutional isomer. Okay, means difference in structure. So there is a difference in structure. So booster and boot camp, they don't have a very detailed video over the constitutional isomer. They just discuss only the nature of constitutional, means difference in structure only. They didn't define the type of constitutional isomer. But in good books like Paula Bruce, David Klein, they have some kind of information. So I discussed this in my video. Okay. So it is important in terms of DAT. So do not ignore it. What about this question number 2? You have two method, RS method and exchange method. I would like to say what is the exchange method for this, means how many kind of exchange here. This is not meso because we don't have a double chiral center, two chiral center, not diastereomer, don't have chiral center. Now you have in enantiomer and here identical. Homomer means identical. How many exchange here? Tell me. Yes, we have two exchange. Two is an even number, means we have exchange between hydrogen and bromine, you can see. And there is exchange between methyl and chlorine. There is a methyl and chlorine. So overall two exchange, two is an even number. Even means identical. Okay. So homomer. Make sense? Tell me everyone, it makes sense? This is easy one. How many stereoisomer here? The formula is 2 to the power n, where n is equal to number of chiral center. So what should be the answer? Yes, two chiral center, this and this. So 4. Very good. Okay, what about this? How many chiral center here? How many chiral center? One, two, three, 4, 5, 6. Makes sense? You guys are quite good in chiral center. Now this is a very good question. This one, 16. It is saying what should be the configuration of C2, C3. But there is no numbering which one is my C2, which one is my C3. So now let me know which one is C2, which one is C3. This C2 or this one C2. Which one is my C2? You have to apply here IUPAC naming. And in IUPAC system, carboxylics have higher priority than aldehyde. So it should be my 1, it should be my 2, it should be my 3, it should be my 4. Make sense? So C2 means this one, C3 means this one. Clear? So it's easy for you now. Rest is very easy. So that's it. So we are done with the stereochemistry. I think I have explained most of the things related to the DAT. So do you have any doubt? You can turn on your mic and tell me. And my next target would be reaction mechanism. And I would like to break down the reaction in two parts. So in reaction mechanism, the first part would be the basics. Because without basics, it's very hard to explain reaction mechanism. And next part would be advanced. In basic, we are going to talk about the reagent. Reagent means electrophile, nucleophile. We will talk about the effect of solvent like polar protic, polar aprotic. We will discuss the stability of carbocation, the stability of carbocation and its rearrangement. This is very, very important thing. Rearrangement. Okay. And I will discuss another thing which is called arrow pushing. Because in this sitting, DAT has changed some of the things. They included a new thing like arrow pushing. So I will explain the arrow pushing as well. So after this, we can jump into SN1, SN2, E1, E2. So this is my request to each and every student. If you're watching my recording and all, please watch all the videos before the group session, like my regular videos. I have explained these kind of things like we have done with the stereochemistry. So I have already discussed the topics like enantiomer, diastereomer and all in my videos. So in the reaction mechanism, very good question. My plan is to upload maybe every day or every alternate day. Till 14, I am quite busy, 14th June. But I will definitely do some of the videos before 14 June, but after 14 June, I would be more regular with my videos and classes. And one more thing, if I'm going to give you any question, then always try to answer them, always, in free time. Okay? Any questions? Please tell me, everyone. And please, if you like my videos, my effort, please, try to tell someone, your friend, Facebook groups. So it would help me. Thank you so much, everyone. I'm going to stop here.